experiment, the RPC are located currently in the middle and outer part of the neon spectrometer and are labeled as a legacy system, and they will be extensively discussed in the next talk by Sinem. So during the high luminosity phase of the LHC, there will be more particles impinging our detectors along with higher rate of background. And the legacy system is not sufficient to cope with and work well with this harsher condition. For this reason, we are going to install an additional layer of new generation of RPC in the inner part of the neon spectrometer in order to improve the selectivity and the redundancy of the trigger. So these RPC are defined to be new generation due to their reduced gas gap width with respect to legacy system, moving from 2 mm to 1 mm. That leads to an improvement of the time resolution from 1 nanosecond to 300 picoseconds. Moreover, these detectors will be equipped with a newly front-end electronics that allows us to work with the low threshold of the order of few femtocoulomb on the electronic signal. So from the experimental point of view, the RPC must guarantee good performances, rate capability, and long-term operation to be used in the ATLAS experiments. So these requirements are fulfilled by operating the RPC in the so-called saturated avalanche mode that is characterized by signal as the one you can see in the green box, so a very short signal with low charge content. Within this context, we have to avoid the so-called streamer signal that are those that you can see in the red box, characterized by a long duration and high charge content. We have to avoid them because they lead to an increase in the current of the detector and a worsening in the rate capability and a possible acceleration of the detector aging. So the pure saturated avalanche mode is achieved historically using the standard gas mixture composed by tetrafluoroethane, isobutane, and sulfur hexafluoride. So thanks to the tetrafluoroethane, we have enough density to reach 99% of efficiency, while thanks to the combined action of the isobutane and SF6, we can work in a pure avalanche mode. Unfortunately, the standard gas mixture has a high global warming potential of around 1,450 due to the presence of tetrafluoroethane and SF6. As you know, the European Union regulation have imposed a progressive phase down of these gases, thus reducing their availability and increasing their cost. Moreover, they represent the biggest contribution of the same particle detector's greenhouse gas emission, mainly due to leaks in the RPC system, legacy system. Within this context, the search for an environment-friendly gas mixture that can maintain the performance of the standard one but with lower GWP plays a crucial role for the usage of RPC in present and future experiments. In order to move towards the replacement of tetrafluoroethane and SF6, we have to take into account two aspects from an experiment point of view. So the first one concerns the performance. So the RPC and operating with the new gas mixture must guarantee very high level of performance under ATLAS irradiation that is around 150 Hz per centimeter square in the RPC region. On the other side, we need that these performances are maintained for the entire duration of the experiment. So we have to reduce the aging effect on the detector. Among the several aspects that affect the aging, I want to cite two. So the first one, as mentioned before, we have to work with low current to avoid this an accelerate aging. And on the other side, we need to minimize the production of fluorine radicals, as widely explained in Liliana's talk. These two aspects are strongly affected by both gas and detector parameters. From gas point of view, we saw that we would like to build a gas mixture with high density and with a component that is capable to suppress the streamer and a general molecular structure to avoid a very high level of fluorine radicals production. Then, additionally, to fulfill the safety experimental requirements, the mixture should not be toxic or flammable. On the other side, we have the detector parameters that represents a strong limitation in one sense because the design of the upgraded detectors is fixed, so we cannot play so much with these parameters now. So among the many parameters, I want to cite the gas gap width. So in particular, the thinner is the gap, the higher the gas density should be to achieve good efficiency. And we already see that we decrease the thickness of the gas gap in the ATLAS phase 2 upgrade. So this will be very important for the next slides. On the other side, we are improving the performance of front-end electronics, so we hope that by lowering the threshold, we will be able to reach maximum efficiency at lower electric field, compensating the production of fluorine molecules. Taking this background, we can move to the ATLAS strategy. So the first action that we call ATLAS Intermediate is already in operation in the ATLAS experiment and consists in the reduction of the tetrafluorethane emission by the introduction of 30% of CO2 in the standard gas. This has the advantage that we don't expect any aging impact because most of the mixture stays the same. On the other hand, even if we are reducing the tetrafluorethane emission, we have the global warming potential is still too high. The only possibility we have is to fully replace these high GWP gas components. We found good candidates among the hydrofluoroolefins family that are low GWP molecules characterized by a double carbon-carbon bond and that are widely used in refrigeration industry. So from now on, the strategy from ATLAS will be divided in 2 steps. The first step I will call short term, because it consists in an upgrade of the ATLAS intermediate solution. So in this case, we replace the SF6 fraction with the chloro-trifluoropropane. The advantages of this approach are the same as before, and additionally, we are starting the fully replacement of the highest GWP molecule in the standard gas. On the contrary, we have still an improvement in the GWP, but the number is still not satisfactory. The second approach, the second step will be a longer-term solution where also the tetrafluorethane is replaced by the tetrafluoropropane. The strong advantage of this solution is that we can build a gas mixture with a global warming potential around 10, that is 100 times less with respect to the standard gas. On the other side, this needs an extensively aging campaign in order to see how the fluorine production can affect the longevity of the detector. This is due to the fact that the hydrofluoroolefins are characterized by this double carbon-carbon bond that represents a weaknesses, so they are easily breaking through the discharge in the gas. So taking these approaches, so the certification of a mixture in ATLAS goes through 2 steps. The first one is checking the performance of the detector under a real ATLAS condition. And then after a selection of the best gas mixture, we can move to select one and start the aging campaign. For this kind of measurement, we choose to study the real ATLAS chamber from phase 2 upgrade. And the results that I will present were very recent, taken in this May 2026 test beam. The measurement have been taken at the gamma radiation facility under real ATLAS condition. I won't go through details of the GIF because it has been already discussed in the previous talk. So let's move a bit to the fresh results. So we'll start with what we call short-term solution. So in this case, we took the ATLAS intermediate solution. We fully replaced the SF6 with the chloro-trifluoropropane. And in this particular case, we explored 2 possibilities. So 1% and 2% of concentration of this gas to see how the streamers are suppressed as a function of this concentration. On the left, you can see the typical efficiency curve as a function of the high voltage for the RPC, comparing the standard gas with these 2 alternative gases. This plot is telling us that we can reach a good plateau efficiency, even if we use add 30% of CO2 in the ATLAS upgrade environment. In the middle plot, we can see the maximum efficiency reached as a function of the chloro-trifluoropropane fraction by operating the detector at ATLAS irradiation background of 170 Hz per centimeter square. In dot lines, you can see the standard gas value, that is the highest one. The other two cases are a bit lower, but this was expected due to the introduction of the CO2. But still, they are very high for the range of acceptance of the experiment itself. The last plot on the right is more an hint for the aging perspective, and it represents the ratio between the current measured with these alternative gases and the one measured with the standard gas at the same condition of ATLAS background. As we can see, the most promising mixture seems to be the one with 2% of HFO fraction. And the most important results of this is that the results are perfectly in agreement with what is observed using the ATLAS intermediate solution. So this means that this gas can fully replace SF6 with no worrying impact on the rate capability and the current of the detector. Last, the second block concerns the long-term solution. So in this case, we replace also the tetrafluoroethane with the tetrafluoropropane. In this case, we focused on the study of the efficiency as a function of the CO2 fraction. So we saw before that in principle, we want to work with as much CO2 as possible in order to avoid a lot of fluorine production molecule due to aging. On the other side, we are working with thinner gas gap. So we want a very dense gas as the tetrafluoropropane in order to reach a high efficiency level. So we did the studies. This gas mixture have global warming potential 10. On the left, we can see the efficiency as a function of the high voltage, again comparing with the standard gas mixture. Even in this case, we see that apart from a shift in the working point, we have a very high efficiency for all options under study. So even with 53% of CO2. In the middle, we have the maximum efficiency as a function of the CO2 fraction, considering the ATLAS background. Even in this case, we observed a slightly lower value of the maximum efficiency, but decreasing with the increasing of CO2. But also in this case, we have values above 90%. It is a very good achievement for the experiment. On the right, we see the trend of the current as a function of the CO2 fraction. Also in this case, we see an increase by increasing the CO2 concentration. And the best option seems to be the gas mixture with 30% of CO2. By the way, the maximum value is 2.2 times the one of the standard gas, achieved with 53% of CO2. And it's difficult to judge this number because just the aging campaign can tell us if we can live with this additional amount of current. So as a general conclusion, we can see that even in this case, we are not seeing a worrying impact in the rate capability and the current of the detector. This leads me to the summary. So I hope I give you a good overview of the strategy for ATLAS upgrade towards the replacement of both tetrafluoroethane and the SF6. So we found two candidates that will be good in the ATLAS context that are the fluoropropane and chlorotrifluoropropane, and both gases showed very promising results in terms of performance. The aging campaign has started for the final certification of the ATLAS experiment, paving the way to the possibility to work with a completely environment-friendly gas mixture.
Thank you very much.
Sorry.
Thanks.
References and thank you for this opportunity. And if you have any questions, I will be glad to answer.
Thank you very much.
Thank you very much.
Yeah, so are there any questions? Okay. So basically, how long would you judge, if I may ask a question, how long would you judge is the time scale until you are finally happy and could put this gas in? Do you think it will be ready for the start of run 4?
This is a very fair question, but it's difficult to answer because the problem with this research in general is that the aging campaign lasts a lot and takes a lot of time. And here there is a very difficult question that is, so in principle at GIF, we can accelerate the aging as we want. But on the other side, we have to find a compromise, because if we irradiate with too much photons, so we are risking to damage the detector, but not in real conditions. So it's difficult to say. We are trying to accelerate as much as possible in order to conclude an aging campaign in around 6 to 8 months. Then we hope that during this time we won't see anything, and to be ready after that. Then also the process to insert in ATLAS is a bit long, but I think all the community will be very happy if they see the results from GIF++, and they will be glad to insert a new gas mixture as soon as possible.
Okay, thank you very much. I think we'll have to move on, unfortunately, but we will still stay with the gases and also with the same experiment. So our next speaker is Sinem Simsek.
Hello.
Hello. We can hear
I
you
will
well.
open my camera just a second.
Yes. So,
Okay,
and
you can see me.
yes, Sinem is also talking about longevity
Yes.
of gaseous detectors as ATLAS. Do you want to share your slides?
Yeah, before starting, I would like to say that, okay, let me make it in a presentation mode. That the previous talk, which my colleagues mentioned, was about the new RPCs, which will be in the cavern and will be a part of ATLAS RPC family soon. But my talk mostly related to the ATLAS RPCs, which is running in the cavern for a long time. So that's I would like to make this clarification. So I can start. Thank you very much for this opportunity. Today I'm Sinem Simsek, and today I would like to mention you the ATLAS RPC eco-gas studies and also sustainability activities. I'm so sorry that you are listening this for the fourth time, but I will be so quick that ATLAS RPCs are gaseous detectors used for muon triggering in several LHC experiments. As a gaseous detector, they are relying on tetrafluoroethane as a main gas and SF6 for the streamer suppression. Of course, these gases were chosen for a good detector performance, like high efficiency, avalanche stability, and low dark current. But as you now very well know, that they have also very high global warming potential, as you can see here. And this was one of the problem. And the other problem is ATLAS and CMS RPC system especially are among the largest greenhouse contributors in detector operations, since they consume significant amount of fresh gas due to the gas leaks in the RPC system. As you can see here, ATLAS and CMS fresh gas consumption plots, their rate ranging from several hundred to more than 1,000 liters per hour. And so even if we reduce the global warming potential of the gas, this alone will not be enough for a remarkable environmental impact. And this brings us to the main idea behind our strategy. Okay, the environmental impact is depending on two factors. Okay, if we combine leak mitigation and gas circulation under the gas consumption, the first is gas consumption, and the other one is the global warming potential of the gas. If we can reduce one of them significantly, yes, we can gain a lot. But if we can reduce both of them in parallel, the overall impact will be much larger. And that's why our strategy is to work on both in parallel. Now, if we focus on only the global warming potential side, there are currently two strategies, two main approaches popular. One possibility is option A, changing most of the tetrafluoroethane with HFO gas based gas mixtures, Therefore, we can achieve a really high or very low global warming potential. And the other option is B, replacing partially the tetrafluoroethane with CO2 and reducing or replacing SF6. The first strategy, option A, is environmentally more ambitious, but it can introduce some serious challenge in terms of detector aging because of HF production. The second strategy is safe in terms of the detector operations, but the environmental benefits can be meaningful only if we can reduce the leaks, because it's still containing tetrafluoroethane, as you can see. For the existing ATLAS RPC system, we chose the second approach and decided to reduce the global warming potential step by step for the detector safety. And for this purpose, first we introduced 30% CO2 and reduced the global warming potential around 19%. And then in January 2025, by halving SF6 on top of this, we reached approximately 27% global warming potential reduction. And this is the current mixture which is used in ATLAS now, ATLAS RPCs now. And later, recently, we are also testing this component R1233ZD as a replacement of SF6, and therefore we can further reduce the global warming potential around 37%. And finally, our long-term target is approach to 50% reduction while maintaining the detector efficiency with this gas mixture. Of course, before being considered for ATLAS, each mixture should be carefully validated before. And for this purpose, we carry out a combined program at CERN GIF++ facility. It's including irradiation, gamma irradiation for aging studies of the detectors and beam test measurements for the detector performance. In this way, we can evaluate both detector stability and physics performance under the realistic conditions. So let me first show you the detector performance, starting with efficiency and streamer behavior with these gas mixtures. As you can see here, of course, one of the most important parameters is the detector performance, efficiency performance for us. Here, I would like to first show you all the previous gas mixtures which we considered, including our current gas mixture, which is shown in orange. And as you can see, after the beam tests, After the beam test, we observed that all the gas mixtures reach essentially the same efficiency plateau, which is around 97%. Only the operating voltage changes or shifts with respect to standard gas mixture, which is shown in blue. So in ATLAS, RPCs are operating in avalanche mode, so we also need to study the streamer mode margin for the different gas mixtures, since we want to stay away from this margin, of course. And on the right, you can see that the current behavior is a function of voltage displacement with respect to the working point. So on this red line, this red line corresponds to the working point, which is defined at 96% efficiency for all gas mixtures. And here, the saturated avalanche model tells us that deviation in this saturation region, we are here in the saturation region, any deviation from the linearity in the current shows us the indication of the streamer. And you can see the behavior of our current gas mixture, which is in orange. Although lower SF6 increase the non-linearity, the ATLAS operating point, which is around 9 kilovolt, which is on this red line exactly, which is here, remains comfortably below this streamer region. So the detector operation is remaining safe. Okay, concerning the timing. Timing is another key parameter for ATLAS RPC, for RPC triggering. in here, you can see again all the gas mixtures which we considered in the test, and higher CO2, we can see that higher CO2 fraction and the lower SF. First, check the higher CO2 fraction. It's improving the time performance with respect to standard mixture, which has 0. And SF6 has a smaller opposite effect, as you can see here. By increasing CO2 and lowering SF6, the RPC time, intrinsic time resolution is improved up to 30% in overall, as you can see. So from a timing perspective, all candidates remain suitable, and our current gas mixture shows the best result among them. So up to now, we saw the short detector performance, but of course, the sustainability is not so meaningful if the detector lifetime is compromised. And that's why we are also performing the aging test. So we performed an aging test with our current gas mixture, and we accumulated 42% of the helium LHC charge target, let's say, before using it in ATLAS. And up to that point, the detector remains stable with an excellent dark current behavior, which is shown in blue, and only with a moderate increase in the electrode resistivity after the initial irradiation period. Now we will see what happened in ATLAS. We also evaluated this mixture, as I said, in ATLAS. And here we are using, for this evaluation, we are using a parameter called calibration current, or iCalib. And this parameter shows the current at the operating voltage when there is no beam, or when there is no beam-induced background. In a stable detector or a healthy detector, it should remain constant or stable with accumulated charge. And therefore, its growth rate should be around 0. And as you can see here, we compare the calibration current growth for the standard mixture and the other two mixtures which we used in ATLAS in different years. And the encouraging results is that with the current mixture, which is shown in blue, the distribution is much more concentrated around 0, with fewer gas gaps showing current increase here. So this is a very positive indicator for the detector longevity, because it says that despite the accumulated charge, there is no current increase in the gas gaps. Our next step is even more sustainable alternative, let's say, replacing SF6 with R1233. So we tested the different fractions of this component, gas component, and first results again are very encouraging. The efficiency measurement again show a very similar detector performance with around 97% efficiency, maximum efficiency for all the considered gas mixtures, with some shifts only. Encouraged by this result, let's say, and a couple of more results, which I couldn't show here because of the time limitation, we also had the opportunity to evaluate this mixture in ATLAS for a short time, when there was no beam, by the way. And the current distribution, as you can see here, between the current gas mixture, which we are using in ATLAS now, and with the gas which has the component R1233ZD, and there is almost no difference. They are behaving really similar, which is a really good promising result for us. On the other hand, we have only recently started the long-term aging, so it's still ongoing. So this is the most important part, maybe, of this presentation, that at the beginning of this talk, I mentioned that the environmental impact depends on two factors. One, this figure shows exactly what is the result of working on both. So the upper plot shows CO2 equivalent emission rate over time, including the effect of both gas mixture change and also leak repairs. Until August 2023, as you can see here, we were using standard mixture. Then we introduced first CO2 mixture as you can see here with orange. Then finally, in 2025, we moved to the current mixture, which is shown in green here. And the gray line shows what CO2, this green line shows what CO2 equivalent emission would be if we didn't change the gas, if we still use the standard gas mixture, let's say. And as you can see, the total CO2 equivalent emission is decreasing after the first gas mixture change, and again decreasing further with the second gas mixture change. And the difference in between them, this gray reference line and these actual emissions, is shown by the green area here. We also take into account the saving from the leak repairs. And for this calculation, we use a reference gas consumption of 1,000 liters per hour, which you can see with the dashed line here. And the gray area in the bottom plot shows again the additional savings achieved saving when the actual consumption falls below this gray dash line. So by combining these two, gas mixture optimization and leak repair, ATLAS has achieved an annual saving of 35 tons of CO2 equivalent. In addition to that, environmental benefit, reducing tetrafluoroethane consumption also represents a significant, as you can see here, a significant operational cost saving. So as a conclusion, to conclude, RPC sustainability cannot be achieved by changing the gas mixture alone. ATLAS chose conservative strategy because it could be implemented immediately and safe. And the key achievement is we achieved already 27% reduction in gas mixture global warming potential. And it's the first concrete example of sustainability-driven detector operation at LHC. And also we obtained this result without affecting the overall detector functionality, which is a really good news. And the next step will be fully validating the new mixture in aging test to establish the best possible mixture for helium LHC or LHC RAM4. Thank you very much.
Okay. Thank you very much. Are there any questions? And I'm a little bit aware of time because we are now almost 10 minutes behind. So I see Jan has a question.
Just a quick one, more of a comment. So with 27% reduction, you're on target with the CERN goals, right? Of 28% decrease. So that's good. And how do you see the HL-LHC running? Because part of these detectors will still be there, right?
How I see, sorry?
HL-LHC running. Are there further improvements that you can do on the system as it is?
For the
beyond
gas
what was
mixture?
shown in the previous talks, of course.
For the gas mixture or for overall in general, you mean?
Both, yeah.
Both.
Maybe
Okay,
if the
as
leak
I told
campaign
you,
can
okay,
improve.
in LS3 we have a very large campaign about both, as I mentioned. We have a new strategy for the leak repair, for example, which is called resin injection or foam injection. Basically, we are using quickly, I can say, expanded foam around the gas leak. So we are trying to surround the gas leaks around the inlets, gas inlets. So by the way, it's now reviewed and it was a successful method. So we will continue to use it in LS3. We will improve a lot for the gas leak repairs and for global warming potential of the gas. We are, as I showed you, we are following another strategy, but at the end we have to find one unique solution for the new RPCs and for us, because the gas system will be one. And that's why we are working in parallel, we are exchanging information. But for now, it seems, let's say, that we will follow this strategy, which I shown. Which I shown here.
Okay, thank you.
Okay, thanks a lot.
Thank you very much.
Thanks again. Let's move swiftly to the next speaker, Muhammad Farooq, and he will now change gears and talk about cryogenic, so cryogenic infrastructures. You want
Thank
to
you.
Yeah.
Okay. Please go ahead.
Okay. Yeah, please go ahead. I'll try to signal when you're roughly at 12 minutes or so, okay? I'll send some...
Sure.
Okay, thanks.
Yeah, I also started my stopwatch. Thank you. Thank you for the introduction. So today I'm just gonna give a overview about the sustainable cryogenic infrastructure and the solid state microwave technology that we use in fixed target experiments at the university scale. And my advisor is Professor Kartzleifer from the University of New Hampshire. This talk is spotted under the DOE, Department of Energy. And that's my background. I'm a second year PhD student in fixed target experiments, and I worked on Higgs analysis, LS experiment, and now working on fixed target experiments in the United States. So these are the contents of my talk about the helium recovery and the liquefaction system and the reservoir of liquid helium and the other solid state microwave technology for DNP system and the sustainability and the operating cost that we have at the University of New Hampshire. So first of all, that's the University of New Hampshire polarized target system that consists of 5 Tesla superconducting magnet that's here, along with the 1 Kelvin evaporation refrigerator, along with the roots pump that help to bring the temperature from 4.2 Kelvin to 1 Kelvin, with the additional liquefier that provides the 500 liters of liquid helium to do our experiments, with additional helium gas bag to capture the boil off from the cryostat, and the helium compressor to compress the gas from this gas bag and then put into the 48 gas cylinders. And then we have a purifier to purify the gas and then send back into liquid helium reservoir to liquefy from helium gas into liquid form. And here we have a recapture efficiency above than 85% in 2026. And we do physics 1 week and the liquefaction from 2 to 3 weeks. And we know the most consumption of helium in industries like MRI, semiconductor and technology, space and defense, quantum computing and ITER. These are the big giants who consume helium. And at major facilities like ATLAS experiment at CERN, LHC, Hall B experiment at Jefferson Labs, Pincus fixed target experiment in Fermilab, and ITR fusion reactor. So all these are major facilities and how they are achieving the sustainability. And as comparison at a university scale, how we are maintaining these figure of merit. So before going into figure of merit and the sustainability, so these are the sources of cryocoolers that we use at university scale for the reliquefaction from gas into liquid form. So there are a couple of cryocoolers in the markets who do this job, like dilution factor, which operates in millikelvin, and Stirling cryocoolers, which operate at liquid nitrogen temperature 77 Kelvin. And we sit around here, Gafford McMahon cryocoolers. So these are the cryocoolers which is affordable at the university scale that help us to go into 4.2 Kelvin and fulfill our requirement for our reliquefaction criteria. And in our lab, we have 2 cold heads that we purchased from the quantum technology from the UK. And it has 2 stage. At one stage, it go from 45 Kelvin, operate at 45 Kelvin, and then lower the temperature into the second stage, which is at 4 Kelvin. And it's about 1.25 watts of cooling energy. So we can see how, which is, it's reliable at a university scale, which liquefy into liquid form from gas into liquid. And here the schematic that I already showed in the first slide, how we are consuming. We consume here in our cryostat, capture through the manifold, compress into gas bag, and then we use the higher compressors to compress into gas cylinders, and then purify the gas, send into dewar or reservoir, and then it's a closed loop, and that's really help us to conserve the and stay at the sustainability footprints. And that's the next SCADA based supervisory agent for liquefied system. So it's a supervisory agent like a HMI that help us to inform the user through the and send all the information into Mattermost and inform what's the status of the liquefier at each stage. So if there is an alarm, it immediately send information into Mattermost and inform the expert. And next, that's the performance and the production rate and the recovery that we have. And in 2024, we recovered 2,520 liters of liquid helium. And in 2025, we recovered 831 liters. And in 2026, from January to June, we recovered 872. All this recovery depends upon the duty cycle, how much we use, how much we do our experiments. And the other additional factor is the production rate, how much we are producing each year. So in 2024, we were producing 33 liters per day, and that was reduced into 31, and now it's reduced to 27.2 liquid liters per day. And I will let you know the reason why we are degrading from 33 to 27 in the following slides. And during the operation, we also lost 200 psi because of the compressor. So there was a vent valve on the compressor, which was faulty, and we lost around 200 psi from the gas bag. And additionally, we can see how much our production rate is consistent from a 26 to 33 over 2024 to 2026. And the higher capacity that we have for our system is 40 liters per day. And the degradation that we see from 2024 to 26 is because of several aspects, like the cold head and the cryocooler's performance. One of the cryocooler is faulty and it is not working well due to the heat load in the room. So we are working on the heat load to install the HVAC system, and additionally the HP compressor and the purity of the purifier. So these are the huge degradation factors in our lab. And the next one is the operating pressures. So normally we are operating the cryocoolers from 4 to 6 psi, and we can see how these are consistent from 4 to 6 psi. So these are the operating or optimum parameters that are optimized for our system. And these are system working well, and hopefully the system would get back to normal optimum production rate after maintenance. And we can see how we consume the liquid from 500 liters and it dipped down to 10 liters, and how we start recovery from 10 liters and then go back to 500 liters. At this stage, we were doing our experiments around 1 week, and we consume a lot of liquid, and we just left around 10 liters. And then after a couple of days, we liquefy from gas into liquid, and we brought back into 500 liters. And then again, we start our cycles to do physics and then reliquefy. So that's the recovery system in our lab. And that's the sustainability scorecard. So if we see the sustainability factor, we recovered around 4,223 from 2024 to 2026. And if we estimate the cost per liter 20 to 30 liters, so we save our money around 85 to 125 Kelvin. So right now, in current market, the per liters price is around 50 to 55 liters per liter of helium. And the major factors are due to the supply from the because of the Strait of Hormuz. These are the reasons of the inflation of the helium supply and the cost. And the next one is about the microwave technology. Why we use the microwave technology? We use the microwave technology to transfer the spin of an electron into proton and deuteron. So at 5 Tesla and 1 Kelvin temperature, electron have a higher polarization because of its magnetic moment. And we use the microwave technology that we call the DNP, or dynamic nuclear polarization, that we transfer from electron to proton and deuteron in the absence of in the presence of external magnetic field. So for more information, you can see my talk that I give at Spin 2023. And these are the major comparison that we have our microwave technology. So there are other microwave technologies like EIO, EIK, and gyrotron sources, which are used at higher major facilities, accelerators, fixed target experiments, and all of those are really powerful microwave source which induce a huge heat load onto a helium bath, which operates at 1 Kelvin. And if we see the helium cost due to this heat load, that's 1.39 liters per watt. That's the helium cost that because of these microwave sources. Main takeaway from this slide is that we have enough power from the microwave that we can do our DNP polarization studies by reducing and maintaining the sustainability factor. And how we are maintaining, I will show in the following slides. So we are ramping the polarization of proton through the DNP effect from 0 to up to 50% or more than 50%. We can see we are increasing the microwave power along the x-axis, and the polarization along the y-axis is also ramping, but at 150 milliwatt, the polarization gets plateau and it's not increasing further. So that means we are achieving our criteria, and this 150 milliwatt is enough for our experiment. And we can see how much the other microwave sources are putting a huge heat load and boiling a lot of liquid helium from the reservoir or from the helium bath. And the next slide is how it also depends upon the power delivery that we induce into the target system. The alignment of the microwave is also impact. If the microwave is well aligned through the tube or the microwave guides, there is a very small loss of helium or very loss of power. And if the microwave is not well aligned, so we can see how much we are losing the helium and how much we are losing the microwave power. So both are also affecting due to the choice of the waveguide, like copper or silver. So these are really better choice for the microwave waveguides that we use in our lab. And this microwave is really beneficial, and at 150 milliwatt, this is fulfilling our criteria and the usage for our studies. And we can see here the further how much heat load we have here. So that's 2024, we have a heat load on the target or a helium bath 0.08 watt, and then 2025 that was 0.14, and then 2026 that was 0.22. And again, if we make a comparison, if we do not have a recovery system, we lost around 170 liters. If we have a recovery system or recapture all the boil off, we have just a loss of 17 liters because of these powerful microwave sources. And the following slide, I just made a comparison how much our microwave system is effective and beneficial. First of all, here the main lifetime and the consumable issue. So this solid state microwave depends on the diodes, which have a lifetime from 3 to 4 years, and then after 3 to 4 years we have to replace the diode. And in EIO case, so cathode tube is also limited due to its lifetime. It depends also on the usage, how much we use the cathode tubes, and also the other EIK and gyrotrons. And the other for the electrical input and the other cooling powers. So for our EIO for our microwave technology, we only need air. And as compared to other EIO, EIK and gyrotrons, these are really powerful and they need additional cooling powers. Like they need chillers or cooling agents to keep cool down because of a higher power. But in our case, we don't need such a higher complex system. We just rely on the air. That's pretty enough for our case. And we can also see how much it is consuming of power. We just need a small power, 10 watts, as compared to other 1.5 kilowatts and the other resources. Sorry, just a few slides left. And that's the scorecard
Yes.
from microwave technology. So we are consuming very fraction of liquid helium as compared to the other microwave technologies. And our solid state microwave technology is pretty good as compared to the others because of the cooling technology and the usage of power. And at the end, we are preparing for these two experiments at the Jefferson Lab for the future experiment to study the spin orientation of the quark in the deuteron that consists of
Yes.
proton and the neutron. Thank you for your attention, and
Okay.
that's the summary. Thank you.
Thank you very much. Thank you very much. I'm sorry we have to wrap up. Are there any questions to the talk? Okay. Again, thank you very, very much for this nice talk. We are a little bit stretched with time, so as I don't see any questions, I suggest we move on to the next presentation and move all of the follow-up questions to the town hall of the Mattermost. The next presentation is by Julien Faivre, and it's on the studying sustainable materials for shielding against ionizing radiation.
Okay.
Okay.
Hi, everyone. Can you see the slides?
Yes.
Okay.
Perfect.
So let me just take a laser pointer. So yeah, just for the joke, actually, we could have named it a study of the MSSM, maximally sustainable shielding material, but this would have been, of course, a bit misleading. So actually, we call this activity SUSHI, like sustainable shieldings against ionizing radiation. Let me try to get rid of this window. No, I can't. Okay. So I will not explain why sustainable here, but why should we get interested into shieldings? Because there are a number of particle accelerator projects. FCC is just one of those projects. And so what I will address in this talk is why sustainable materials could be interesting. And I will show some preliminary results for photons. I can spoil actually the end. Of course, the shieldings, such shieldings will be worse than the current materials because we already have the best materials. But we cannot address the climate change without heavily changing the way we do. And therefore, for me, these questions can rather be expressed as how much worse do we do with sustainable shieldings, and what are the new constraints which appear when we use these materials. The whole story began with these kind of pictures, which most of you know, at CERN or elsewhere. Some big blocks of concrete are used to shield against particles, and we can build structures with these blocks. But this can also be done with sustainable materials, blocks here, sorry, and structures built with these blocks. If you look at these pictures, it just looks the same. So why should we be interested by sustainable materials? Because low carbon concretes are still under development, and in any case, their CO2 emissions are not zero. While for sustainable materials, the techniques are already well known and they are mastered for building. A second family of argument is that concretes use resources like cement, sand, and gravels, but also metal, which is associated to the use of concrete. They need transport, and they generate quite some gray energy. While for earth, for example, raw earth, the resources are abundant, they are local. Earth is made of, it already contains the right amount of sand and gravels. It needs no crushing, no heating, about no transport. And we already know that, for example, next to CERN, we have this resource available. And a third argument is that when you look at the whole life cycle, actually concretes have an irreversible setting because it's a chemical setting. So this makes them not recyclable. They need transport and crushing again, etc. And so for the end of life, sustainable materials are better because they can be reused because the setting is reversible. So this is a picture of literally recycled building. It was I mean, an aperture has been made in a building and the earth has been used to build another building. Otherwise, you can also destroy on site. Because the earth was not chemically modified, so it simply returns to the ground. So I talked about earth, but also vegetal fibers could be interesting because they contain hydrogen. But let's focus on earth for the moment. Why can earth shield? Because the ingredients of concretes, so earth is an earth concrete actually, the ingredients of concretes are the same. They are clays, so they are raw for earth and heated for cement concrete. And there are also sand and gravels, which are added in one case and which are already contained in earth in the other case. So you have the same chemical elements and you expect to have similar densities and therefore the same shielding or a similar shielding. Now, the first part of this task is to understand what material is earth, and therefore you have to look into the composition of sands and gravels, for example, and of the clays also, and you can notice that there is quite some variability. And of course, this has a consequence in terms of shielding because it changes like the average Z of the material. Another variability is that different earth do not always contain the same amount of clays, for example. And other sources of variations in atomic densities are the humidity of earth and also, of course, the density which you reach when you are making this material. So all this enters into, for example, if you look into what's going on for photons, it enters into the Linux attenuation coefficient. You can see the density, the atomic density here, and the Z composition, which enters through the cross sections. This is the attenuation coefficient as a function of the photon energy. And the interesting thing is that in the area around the MEV range, photon interactions are dominated by Compton scattering. And this looks to be independent of the material. So we made a bit of calculations with the tabulated values. We also calculated some variables like the thickness needed to obtain a given flux reduction. And we made some samples also to test experimentally. And this is what we obtained. Pay attention to the fact that this is still work in progress. But basically, if you look at this, this is the attenuation coefficient as a function of the photon energy. Indeed, we find that the composition is not so important. It becomes more important at low energy where the photoelectric effect begins to dominate, but there the attenuation is very strong, so we are less concerned about this area maybe. We obtain a similar result for earth humidity. If you increase the mass content, you also increase the number of atoms and therefore of shielding. But what we found out is that the by far dominant factor was the density. And since standard concrete is more dense than earth, well, we have to put more thickness to obtain the same shielding. The good news, or what I think is a good piece of news, is that apparently only 20% extra thickness is needed to obtain the same shielding. So it's not like we have to double the thickness of the material. It seems affordable. And we also checked this experimentally and things work. The second result about photons in the MEV range is that if you look back to this curve, you can see that hydrogen is a particular material around the MEV range because of the Z over A ratio. And so one natural question could be, can we achieve the better absorption in this energy range if we enrich the material in the hydrogen? And you can do a bit of math and you find out that it is actually not possible, but because there is no material in nature that can achieve a high enough hydrogen content to do this. We also checked with the database values that these results still hold, and also experimentally. And the last result I wanted to show is about the interaction of photons of higher energy, now GeV in this case. Such photons will make an electromagnetic shower in the material, and this formula allows to calculate the length of the showers. So we plug in there the material density and composition. And what we find out is that, again, the driving factor seems to be the density. And we find again that the length of those showers is about 20% longer in raw earth with respect to concrete. As a conclusion, I think that this shows that sustainable materials can be relevant for shielding, at least in some situations. For the photons, the price to pay seems to be an extra 20% thickness. And as per the prospects, we have a few technical matters to think about. But in terms of shielding for itself, we have to see the hadronic showers to take interest also into the activation. We already have some positive signs in these directions, no real worries. But what we did 2 weeks ago is that we tested with neutrons in the MEV range. So we took Earth from a door or window that was created in a building. So it is recycled earth, and we used it to build bricks with the rammed earth technique. And on the other hand, we also use this earth to mix with straw to create bricks enriched in hydrogen, which is important for neutrons, of course. And we put that on a neutron beamline to irradiate and see what happens. And so we did a week of data taking, and we have a lot of data analysis ahead. And so I hope that next year I will be able to show you some preliminary results about this.
Okay, thank you very, very much. This was a really interesting talk. I guess you cannot tell us anything about preliminary analysis yet.
No,
but maybe there's
because 2 weeks ago is really so. I mean, we don't even have any stuff like preliminary.
Yeah, but I see there's questions by Shayasi.
Very preliminary. What is gray energy? You mentioned in one of the beginning slides.
Yeah, gray energy is the energy which I don't remember the very exact definition, but it's like the energy which you need to build the thing.
Okay.
For example, here, if you want to build a carbon block, a concrete block, it's the energy you need to build it.
Okay, thank you.
Okay, then I see Hannah has her hands raised.
Thank you. Thank you for the interesting talk. So something that we worry about in terms of radiation protection in concrete is long-term, basically it losing some of its water content and being less protecting. I wonder, have you thought about the temporal impacts of using earth and whether it works long-term as a radiation shield?
Why? No, I was not aware. Why is water a problem for concrete?
If I seem to remember that there's potentially like a 60, 70-year lifetime for a piece of concrete shielding in terms of it.
Okay, really for the lifetime of the material by itself. Okay.
Yeah.
So yeah, there are two ways to answer, or let's say two pieces of answer. The first piece is if you see this building, it is 200 years old and it is still there. So we know that this technique works in the long term. Now, the other piece of the question is the activation. Well, I should not say activation. It's more the irradiation problem, because when there is water, you make this radiolysis of the water and you create free radicals, which can chemically act on the material. So I presume that what you refer to is a consequence of water hydrolysis on the concrete. And indeed, it would be part of the task to study what is the effect on Earth.
Okay, yeah.
So no, sorry, yeah. Just to complete the my answer, if the block is damaged, it is recyclable.
Mm-hmm. No.
Okay.
I guess, sorry, just to clarify. So if like over a long period of time, there is, you know, the water content does reduce, does that not impact its protection against neutrons?
No, it does not reduce. It is like it changes, but it changes with seasons and weather. But it never gets to zero. Otherwise, the block does not hold anymore. You need to heat to hundreds of degrees to make the completely disappear the water.
Mm-hmm. Okay, thank you.
Okay, thank you very much. We'll now close the session on detectors and sustainable materials, or sustainable detectors and alternative materials. And we'll move on to the second session in the conference on large-scale projects and policy making. Chandramouli Agrawal will take over the moderation.
Thank you, Kristen. So I would like, can we have Falastine Abusaif for his talk on assessing sustainability performance in large research infrastructures?
Yeah.
Yeah.
I hope that you can see my screen.
Yes.
Okay. So, hello everybody. My name is Falastine Abusaif. I am from Karlsruhe.
Would you like to go in the presentation view? We can see.
Yeah, I did. I did.
No, we see all the slides.
Okay. How about now? Do you see it in the full mode?
No.
That is strange because I am sharing the full mode screen.
Maybe we can continue then.
Yeah, if you want, I can stop sharing and start again, but
sure, maybe we can try that once.
Okay, but you can see the full screen, right?
We can't see the full screen. We see the sets of all the slides in your
okay,
PPT.
so I will stop sharing and again try it again. Hopefully it works. Okay, I tried again.
It's the same, but maybe we can continue. It's all right.
Okay.
Yeah.
So, as you know, my name is Falastine. I am from Karlsruhe Institute for Technology, KIT University, and today I will be talking about assessing sustainability performance in large research infrastructures. So I will present to you a sustainability framework that has been developed recently in order to enable users and facility operators to quantify and measure the sustainability. And this activity evolved from the efforts of a Horizon Europe project called Research Facility 2.0, and I will be talking on behalf of the project. So we are talking about large research infrastructures.
Sorry to interrupt. Have you moved on to your next slide?
Yes, I did.
We are still seeing the title slide.
I am in the next slide. I don't know what's going on.
May I suggest something?
Yeah, you can share my slides if you want, and
just don't go in full screen mode. Now we can see your second slide. So just stay out of full screen mode and just continue that way. Yeah.
I hope that this panel does not bother you, so I will just minimize it. Okay. So we are talking about large research infrastructures. They are important facilities for the society because They are delivering interesting science and interesting discoveries. But nevertheless, these are facilities that are well known to be energy-hungry machines and resource-consuming machines. And this is what I am trying to highlight on. So if you look at the left side, the plot here manifests the annual energy demands of some international facilities during the year 2024, according to their own reports. We can clearly see that the annual demands are exceeding several hundreds of gigawatt hour, and sometimes if we compare it with a small scale city, it is even more than the demand of such cities. However, the image about the energy and the electricity demands alone does not give us a full picture about the sustainability assessment. We need to consider other parameters, and this is what I am showing on the right plot. So here I try to reconstruct the indirect CO2 emissions associated with the same facilities during the year 2024. And one very important feature that we can see by simply comparing the two plots on the right and the left is the fact that some facilities, despite having lesser annual demands, they are producing more environmental impact in terms of CO2 emissions. And this is clearly attributed to the fact that they are driven from different grid operators, and the carbon mix is definitely different. So this reminds us of a very important fact. We cannot look into one single parameter or one single dimension if we want to assess the sustainability. We need to have a full picture about all the environmental effects. How should sustainability be assessed? We are facing more than one challenge. The first challenge is related to the sustainability and how it is multidimensional, which is the thing that I just highlighted on in the previous slide. So environmental performance cannot be triggered by looking into one dimension. So if I want to highlight on the utilization of resources, then we will be reminded directly of the waste generation. And if we mention waste generation, then we are reminded of the occupation of land. If we mention land, then we are reminded of emissions and so on. So it's multidimensional, and all these dimensions need to be considered in order to have a fair assessment. The second challenge is related to the nature of large research infrastructures themselves. So they are the home of delivering science. Unlike industrial facilities, these large research infrastructures are producing scientific value. This raises another question: how can we simultaneously evaluate the environmental performance together with the scientific performance? So we need to resolve this. The third challenge is related to conventional, well-known approaches in assessing sustainability. And if I want to mention... Sorry? If I want to mention, for example, life cycle assessment tools. So they are well-known approaches for assessing sustainability, and they are one of the most common and internationally recognized. I do appreciate such tools. They are really valuable. However, they are linked to some uncertainty, marginal uncertainty and sensitivity linked to the selection of databases, selection of data repositories, and so on. And they also tend to not put a lot of emphasis on the value of the scientific output when the performance of scientific research infrastructure is addressed. So all of these challenges, they motivated us into developing a new systematic framework that address all these challenges at the same time. So we have developed a systematic one that is multidimensional, that is directly linked to the scientific value of research infrastructure, and that is operationally targeted. Here, I would love to show you the schematic of our developed sustainability framework. So as you can see here on the right side, it's divided into 3 main domains. We are having the resources, the energy, and the emissions. And these are conventionally known to be the factors that are putting a lot of pressure into the environmental aspects when the evaluation of the operation at research infrastructure is considered. Each of these 3 domains is divided into several subdomains. And again, similarly, each subdomain is divided into further indicators. So in the 3rd layer, if you look at the 3rd layer of the hierarchy of the model, where you can see the little triangle that are either colored with black or white, this is the layer where the sustainability indicators are lying. Here in the framework, by default, we defined a set of 22 high-level sustainability indicators, but the model is flexible and it takes into account the case study itself or the assessment that one is performing. So it can be more or less than 22, depending on the context itself. One very important aspect of the developed model is the fact that it does not look into sustainability as abstract values. Instead, it evaluates the sustainability in terms of some reference output. And this reference output either defined as a unit of time or a unit of scientific output. So let me now introduce to you 2 main scientific distinction for the developed model. In the conventional assessment, usually the environmental assessment is done by looking at the impact per unit of time. So we evaluate how much emissions annually, or what is the material use in 1 month, or what is the energy demand, let's say, in 1 operational hour. So it's always referred to a unit of time. This is very important, and we do adopt this, but we also adopt another thing in parallel to the unit of operational time, which is the unit of scientific output. So along with the operational time, we have energy per science, emissions per science, material per science, just as an example. Apart from that, also the developed model is taking into consideration the energy management sector. So we have, under the energy domain, we have defined a subdomain and called it energy management sector. And some indicators are defined underneath the energy domain, for example, the energy recovery, self-sufficiency ratio, and so on. These indicators, by convention, they refer to the facility operation itself, and they do not necessarily require the weighting with respect to some particular output. So in a nutshell, I can summarize that the framework is collecting 3 different categories of indicators. Some of them are let's say, weighted with respect to time. Others are weighted with respect to the scientific output. And a 3rd category, which is looking into the facility directly. This enables us into performing the environmental assessment from different stages, components, system, subsystem, or even the entire facility level. Now that we have talked about the distinctions of the model, let me introduce to you the deployment of such a framework. When we developed it, we also prepared alongside a mathematical terminology that describe how such framework can be utilized and implemented in daily research. So the first step starts by defining the scope of the assessment. So we ask ourselves, what are we exactly assessing? Is it the entire facility? Is it like a technical design, a component, and so on? The answer to such questions should define the type and the number of the indicators, the metrics that need to be considered within the assessment. And of course, once we define the indicator list, we move towards the 3rd step in the mathematical terminology, where the normalization is essential here, because we are looking into metrics that are having units. So it makes no sense to compare at the end bananas with apples. So we need to bring them all into the same floor, and that's why here normalization is essential. After that, we give them weighting depending on the hierarchy level, and we aggregate and finally arriving at some sustainability scores. So we end up from having a set of units, or let's say a set of indicators with some measurable units, into having a sustainability score that is unitless. It can be here, so I call it SS sub N, which denotes the sustainability score, and N here denotes the three main domains in the framework, either emissions, resources, or energy. If we want to have an overall picture about the three main domains, then we need to calculate the SS overall. Just for you as an example, because we are talking about the implementation of the framework, I show you here a case study about the practical implementation. And it was applied on a set of electromagnets, like dipole bending magnets used traditionally in some accelerator facilities. And so the set of alternative designs were generated and simulated with three-dimensional film analysis. And once we got the physics output, the numbers that we need in the sample space, we applied the framework, we calculated the sustainability indicators, and eventually we ended with the figure that you can see here. So this is the three-dimensional sustainability space with the three axes representing the sustainability score along the emissions, energy, and resources. The color code here represents the overall sustainability score. So I tried to highlight with the dark red area, just to show you this is the location where we have a compromise, an idea about the three main domains of sustainability, which should be like the most environmentally friendly designs. The idea behind showing this plot is not just to tell you that, oh, we have ended up with some fabulous magnet for accelerator facility. No, the idea is to show you that this is how sustainability assessment should be done. We need to consider this at an early stage in the planning, and we need not to target one particular direction. We need to have a fair idea that describes all the three dimensions. This should bring me into my conclusion slide. So I did not put many sentences here, and I just have one single take-home message for you, which is what cannot be measured cannot be managed. So you need to have your numbers in one hand so that you can manage it properly with your other hand. So thank you very much. I hope that I respected the time. I see that it's -3. I don't know what does that exactly mean.
It's all right. I love the quote that you mentioned, what cannot be measured cannot be managed. Do we have any small questions? Lengthy ones we can take over on Mattermost. Do we have any very small questions? Okay, we have one by Hannah. Okay.
Yes, Hannah.
Thank you. That was, I mean, it's really interesting. I've read about this a little bit before. I think what I find interesting is, so you've turned this into like almost a three-dimensional comparison. So you have your three axes, but within those you have a lot of different variables in terms of land use and radiation and all of these different impacts. So if people are comparing these different overall impacts, but can't really see into like where they came from and what weight's been put on the different impacts, how, when we compare, do we like avoid I guess misinterpreting and perhaps like maybe not representing that information well enough?
Yeah, that's your question, right? It's a concern rather than a question, I would say.
I guess, yeah.
Yeah, okay, I totally agree with you, but you need to be relieved because so the reason behind showing the three-dimensional sustainability space is in fact more than one reason. First of all, I have in total 10 or 12 minutes, so I cannot go into further technical details. And another reason, yeah, what you mentioned is very important, and for transparency, it has to be shown and clarified. But this is not my message. My message was to show you that this is how sustainability assessment should be done at an early stage. So we need to have a full picture that describes all the dimensions. But of course, if you want to dig deeper and see where are these scores coming from, of course, one need to understand the details. It was based on applying the full mathematical terminology, introducing the indicators. You mentioned land. And here in this assessment, I did not rely into introducing the land as a sustainability score, because I am evaluating a subsystem level. It's bending electromagnets. We are in the subsystem. So the land is coming into play. If we were talking about the facility level. The choice of indicators is freely defined. So the type of the assessment should define how many indicators should come into the play. So in this particular study, I considered the material per operation. I did also consider the material per science, the energy per operation, the energy per science. I considered as well the emissions per operation, the emissions per science. I subdivided the material per science into the variable level and calculated, for example, 3 different units for the scientific output. I had the nominal magnetic operational feed. I had the bending power of the dipo itself as unit of output, scientific output. So I did like deep, detailed technical assessment. And of course, it's very important. It is very important, but this was not my message. I was trying to highlight on the very big picture of how sustainability should be assessed.
Yeah, I think
Thank
Hannah got
you.
the message.
Thank you. I will, I'll follow up afterwards. I'm
if
interested
you're
to talk more. Yeah.
Yeah,
Thank
okay,
you.
we can get in contact if you want to know more technical things.
Thank you, Falastine.
Yes.
So next up, we have Nuno Elias, and the talk is on developing a roadmap for sustainable cryomodule design. We
Yeah,
can see your screen and on full slides. Yes.
Yeah, you can see
Please.
my screen?
Yes.
Perfect. So thank you for having me. My name is Nuno Elias. I work at as a lead engineer, cryogenic engineer at European Spallation Source. I make sure the accelerator Cryomodels are operational, but I'm also work package 5 lead for the ISAS consortium. So today I'll be presenting our roadmap for sustainable Cryomodule design, project financed by the European Commission under the ISAS program, and walk you through integration efforts in work package 5 and our future implementation strategy. So sustainability is a priority in particle physics, as highlighted in the 2020 European strategy and subsequent calls for climate-friendly research infrastructures. ISAS was born after the EU call new technologies and solutions for reducing environmental and climate footprint of research infrastructures. So ISAS stands for Innovate for Sustainable Accelerating Systems, launched in 2024. It has a budget of 13 million euros, 5 of those funded by the European Union. It counts with 12 research institutes and 6 industrial partners, and about 1,000 person months spread over 4 years. And now we are in the middle of that project. So to improve sustainability, we must analyze the entire energy chain. In superconducting RF, there are multiple sources impacting the grid to beam power efficiency. So including efficiency from the RF sources themselves, the RF load and the tuning of the cavities, the cavity losses that then have an impact on the cryogenic system, how you then refrigerate those cavities, and for example, the coefficient of performance, which is a measure of efficiency of the cryogenic plants, and also the loss of the beam power when you actually need to dump the beam. So in ISAS, we are looking at the ways to increase that efficiency, and we have different ways of doing that. So here at this slide, we have a few mitigation strategies. So basically, we are organized in work packages that will look at 4 technology areas. So starting from work package 1 to 4, where we look at technologies such as ferroelectric fast reactive tuners, optimizing low-level RF, improving cavity efficiencies with different films so that we can operate at higher temperatures, improving couplers and fundamental high-order modes couplers. So across those technology areas that are being developed, then we have integration activities. So I'm working at work package 5, so which is an integration activity that looks at those technologies, and we try to integrate them in the design of a new energy-saving cryomodule. There is also other integration activities, or package 6, that will integrate those technologies in current or future research facilities, and also our package 7 that will look into integration into industrial solutions. So work package 5, as you know, any LINAC cryomodule is optimized to meet specific research objectives of the accelerator facility while addressing common challenges such as high power electric fields, ultra low temperature, ultra high vacuum, precise alignment, etc. So what we want to do with work package 5 is to tackle the common engineering challenges of integrating ISAS technologies into the parametric design of a new cryomodule, building on the developments made with the ESS cryomodules while benchmarking against other facilities. In addition, to unlock the full potential of the energy-saving capability of this cryomodule, also part of the work package 5 is addressing the challenges of beam dynamic requirements, such as operating the new cryomodule in energy recovery LINAC. So this is a parallel activity that goes into beam dynamic studies. So here are the main tasks of work package 5. So it's subdivided in 4 tasks of coordination, and then we have 2 tasks, which I will talk about today, which is ESS cryomodule experience and benchmarking with other facilities, and then generating a sustainable criteria for LINAC cryomodule design. So the first activity that we had was actually the first half of the project was to conduct a deep dive of the life cycle review of the ESS high beta cryomodules. And here we have just a picture showing the different families of cryomodules that we have, but we focus in high beta elliptical cavity cryomodules. So we conducted this lessons learned activity, and the main goal was to create a report with these lessons learned that then will be fed into the benchmarking with the different facilities. So we looked at the complexities of in-kind institutional manufacturing and initial operation, and we've documented these technical pain points that currently drive inefficiency. So here I have a picture of one of cross-section of one of our cryomodules, that's to show you that the cryomodule is basically a masterpiece of multidisciplinary integration. It basically goes across cryogenic, RF system, vacuum, mechanical alignment, and which are essentially competing for space, but must work effectively together. So when we talk about optimizing for sustainability, it requires balancing these highly sensitive interdependent systems. So we also looked at the cryomodule qualification process that we do at ESS. So here I show you one of a timeline of what it takes to test one of these cryomodules and qualify. So we look at the performances, which I will show you in the next slide, but also we'll look into non-conformities during this activity. And then these non-conformities will be then the baseline for requirements of our new sustainable design, ensuring that we will avoid these pitfalls in the future. For example, in this plot, I show you static and dynamic and total heat loads of cryomodules tested for the ESS accelerator, and we also compare these real life heat loads with what was estimated initially in the design phase. The gap between what is estimated and the real world heat loads is a major point when defining and designing and sizing a cryo plant, because these are then costs that we'll have to commit for the future of the facility. So on the design stage, if you have a better knowledge and better margins about what these heat loads can be in the future, you can size better your cryo plant and then have lower energy costs in the future. So we also looked at the integration of these cryomodules in the tunnel from installation and commission point of view. I will not have time to go through all the points, but I can show you here that we have just presented the lessons learned from the ESS elliptical cryomodule design operation at the International Cryogenic Engineering Conference in Daejeon in South Korea. So if you are interested, you can go and look at the paper that we presented there, but I have more information for you. So after these lessons learned, we actually benchmarked against, sorry, I'm just checking the time, against other facilities. And to do that, we looked at 5 different key areas to benchmark against. So from beam and RF parameters, cryogenic systems thermal management, cryomodule design, commissioning insights, operational experience, and reliability. So we defined what were the questions that we wanted to ask and benchmark against. We pre-filled this questionnaire that to be sent to 6 different facilities with data that we found already on the literature. And then we had face-to-face interviews with the experts of these facilities to actually help us just mostly focusing on the lessons learned from the design phase. And these are things that sometimes you don't find in the literature. So we wanted to have really the one-to-one discussions going deeper into the problems that were faced and the problems that could have been avoided in the initial phase. So just to give you an idea here, so we looked at 6 different facilities across the world to compare against the ESS cryomodule. ESS, SNS, LHC, LC, LS2, PIP2, and XFEL, and an idea of the diversity of the types of cryomodules that we analyze. As you can see, there are multiple solutions for cryomodule integration with different thermal shielding, different cooling loops, and different spatial integration. And these differences come from specific requirements from each facility and the historical trade-offs. And the main challenge of Work Package 5 is to analyze this design spectrum and extract the common denominators that allow us to standardize sustainability regardless of the facility's specific operational needs. So I will not have time to go into the detail about the fact, but I can just pinpoint findings. So here I show you a little bit of a summary of each one of the different key areas that we looked at. So for example, for beam and RF parameters, we color-coded each of the facilities, and then we have a description of the differences and what is actually the same for each one of the facilities. But what comes out of this is that continuous wave machines prioritize IQ, so the quality factor of cavities, to minimize dynamic heat losses, whilst pulse machines prioritize towards higher peak gradients in the cavities. And also we have a wide range of power coupler power, and mainly two different families and integration in the Cryomodule, where these power couples can be placed in the vertical orientation or horizontal orientation. And also for proton linear accelerators, the beam exhibits a very low sensitivity to trapped HOM perturbations. Okay, so the time is about to finish. Okay, I'll accelerate. So then in terms of cryogenic system and thermal management, one important aspect here, okay, every Cryomodule has a multi-level temperature architecture, but one important point to take out is the cryogenic distribution strategy. Some accelerators go into a continuous accelerator strategy, and while some others have a segmented approach where Cryomodules are individual systems where the beam diagnostics are placed at room temperature. In the Cryomodule design itself, we have seen variations in cavity supporting schemes, variations in magnetic shield implementation, design compromises, and the integration of multiple thermal shields or a single thermal shield. So there is actually a big variety of implementations, but also we are seeing a trend towards including access hatches for mitigating failures once in operation and to allow for maintainability and repairability in situ. So then we had big discussions about commissioning insights and operational insights. I will just jump over this slide, sorry, because we are running out of time. So basically here, just to say that we have really went deep in trying to check with the experts and trying to get to the nitty-gritty details of each one of the Cryomodule designs. And we have created a report that is accessible in archive. So this report compiles the ESS lessons learned and the benchmarking of facilities in the implementation phase. And we have two annexes to two different detailed reports about this. So they are about 70, 80 pages long with very important insights. So from these lessons learned and from this benchmarking with different projects, we are now entering the second phase of our project, where we want to do a parametric design of a sustainable cryomodule technologies. So now we are looking about what parameters are relevant to compare, and what is the desired and achievable degree of complexity that we can get at the end of this project. So we have 2 years to go. So we are trying to figure out how detailed we can be in our analysis. Then regarding the design, we are looking at what are the design drivers of Cryomodules, what are the design requirements, what are the design constraints, what is the inherent uncertainty on the Cryomodule design, what are the typical best practices, and what are, if people are following or not, systems engineering approach. And if there is any design dilemmas, what are those dilemmas when having to decide between two things that are good or two things that can create problems. So looking at the sustainability aspects, we are mainly focused on energy saving aspects, but we also look at the full life cycle of a Cryomodule, looking at the availability, maintainability, and repairability. And now we are involving in industrial partners, so because we think that having an industrial approach
could you please summarize in
yes, it's the next slide. So industrial solution can actually be beneficial to actually for sustainability. So I will just summarize in the next slide. So ISAS initiative is establishing new technologies and the roadmap for next generation high energy efficient superconducting accelerated design. We have performed a comprehensive benchmarking with various facilities and identified critical parameters driving thermal efficiency and operational reliability. We identified the key drivers for sustainability being standardization, modularization, industrial readiness, collaborative governance, and optimized design trade-offs. And now the future outlook of the upcoming phase into the parametric design framework. I would just like to thank your attention, and special thanks to our Work Package 5 colleagues and all the partners involved in this project. Yes.
Yeah, thank you very much. We will be not taking any questions. They can be taken up on Mattermost. We are already running short on time. So I'll call the next speaker, Mr. Michael Sparks, who will be talking about exploring ECS for energy-aware parallel research software. Yes, we can see your screen. Yeah, right.
And you can hear me, I'm sure.
Yeah, we can hear you. Please go.
Okay, I'll go. Hello, I'm Michael Sparks. I'm from the University of Manchester, and I'm here with Delano and Evans to present our work on exploring ECS for energy-aware parallel research software. So the problem is that physics workloads are increasingly parallel, and parallel programming remains hard in practice. Parallel hardware is now standard: CPU clusters, GPU clusters, supercomputers, accelerators, laptops. System design practice and teaching, however, remains linear. So scalable systems end up fragile and hard to learn. So this is about improving and widening the utilization of modern infrastructure. So the hypothesis is that entity component systems may provide a route through this. And what is that? So ECS is a model from media, film, sound effects, special effects, and games. It separates data from behavior. You have entities that hold components. Components can be things like velocity, position, and so on. Systems can process many entities under shared rules, which means you've got naturally concurrent environments. That simplifies large simulations and makes later parallelization easier since the code is naturally concurrent. Whilst it's common in media, it's inspired by physics, which leads to an irony that ECS is largely unexplored in research computing, bar exceptions like atom ECS. So GreenPhysECS asks whether it can help early career researchers build scalable physics software from the outset. In terms of implementation, there's a bunch of different stuff it uses: C++, 20, Flex, RAPL, Docker, those sorts of things. Main time constraints is implemented by 2 MPhil students with very limited time using heterogeneous hardware, needs to be reproducible and practical. So there's a couple of constraints which have been put in place for practicality reasons. There's links which I've put elsewhere. Also, testing this hypothesis really requires real work. So their work has been primarily around fluid dynamics and epidemiology and general investigations for outbreaks in crops. So I'm now going to pass over to Oluwole to carry on.
So as Michael said, the first project we worked on was in fluid dynamics. Next slide. And we chose fluid dynamics because the computational fluid dynamics is a very well-developed field. There are a lot of very well-studied techniques, and this allowed us to have a good basis that we could try and apply the ECS model to. And the 2 techniques we considered were the finite difference method and the smoothed particle hydrodynamics. So when you're considering a fluid simulation, there are 2 ways that you can picture the fluid physically. There's the Eulerian approach, where you consider a fixed position in the fluid and consider how the fluid moves past that point. And there's a Lagrangian approach, where you consider a fixed parcel of the fluid flow and follow that parcel as it moves through the fluid. Next slide. So the finite difference method is an approximation method that's based on the Eulerian view of a fluid. It approximates a continuous domain by a set of discrete points that make up a grid, as shown in the figure on the right. And then derivatives of a function can be approximated by evaluating a function at neighboring points on the grid. Next slide. And in smooth particle hydrodynamics, this is a Lagrangian approach to simulating a fluid. And this approach works by approximating the macroscopic properties of a fluid, such as the density or the pressure, based off the way the fluid elements are spatially distributed. And this ultimately results in having a very simple equation of motion that you can apply to each of the particles in the fluid. So to make this approximation of a fluid based off the distribution of fluid elements, you consider all particles within some radius h of each other, and you sum over the particles to approximate a certain property, and an interpolation function is used to weight this sum. So for example, the density sum is mass times the interpolation function. We implemented this, like we said, using the ECS model. For the finite difference method, we represented entities as points on the grid, and the components of each entities were the values of fluid parameters at that point, so velocity and density for the FDM. And then systems that are applied to these entities and components evolve these properties according to the discretized Euler equations. Then for smooth particle hydrodynamics, the entities here were particles in the fluid, and then the components were the position, velocity, and acceleration of each particle. And the systems were used to implement collisions between particles and apply the equations of motions to evolve the state of the particle. Here we have the results of these two simulations. On the left, we have a graph showing the evolution of the density field in the finite difference method case. And we can see the fluid evolving through the medium over time. Here we're considering two boxes connected by a slit in between them. And on the right, we have a graph from our smooth particle hydrodynamic simulation, where we are considering, again, the same system, but here what we've plotted is the change in energy of the system over time. That's because we calculate the energy of the system at each time step from the kinetic energy of each particle. And this change in energy is obviously not physical, because in a real world situation, the energy of a closed box wouldn't change, but it is a result of the approximation. It's an artifact of the approximation. So energy tracking was implemented to this phase of work, and this was done by adding a system to the start of our program that basically started the energy tracking, and then a system right at the end that closed or bookended the energy tracking. And this was a very general structure, which means it can be applied to any other program made using the ECS model. And it was a good proof of concept for this, but we still need to apply it to further work. What we learned from the fluid dynamic simulation was that the ECS model works very well when you have many entities that have similar properties and you have a dynamic system. So for example, in the smooth particle hydrodynamic case, it worked very well for simulating many interacting particles. And it could also deal with time-dependent fixed position differential equations, as was the finite difference method case. The cons we found was that for static cases in the finite difference method, the ECS model wasn't well suited to solving matrix problems, and conventional methods were better there.
And then in our second project, we looked at doing simulating Markov processes. Markov processes are essentially memoryless stochastic processes. So the probability of moving to different states depends only on your current state, not any previous memory history of your state. This got wide applications, and there are multiple approaches to solving them. But in this project, we looked specifically at algorithmic approaches. And the algorithm we used in this project was the discrete time algorithm, which we can move on to the next slide. So in the discrete time method, you first need to determine all the possible transitions between states. So in this example of a very simple two-state Markov chain diagram, you have these transition elements between state one and state two, or within the state, which is given by the probability of being in some state n, given the previous time step you were in state m. The algorithm is as follows. You start with your initial state, say state one. You then determine all possible transitions. So you could stay in state one and move to state two. You draw a random number between 0 and 1, and based on that number, you could choose a transition. Say you move to state 2, and then you advance your simulation by a time step and return back to step 2 in your new state or the same old state. And you just keep doing this and you get a simulation. You can do this multiple times to get an ensemble, and you can get things like a mean and standard deviation. Moving on. So we applied this to epidemic modeling specifically. The most widely used, or the most basic epidemic model is like the SIR model, which is called a compartmental model because it splits the population into different compartments such as susceptible, infected, and recovered. People who are susceptible can move to the infected category, or they can stay susceptible. People who are infected can move to the recovered category, or they can stay infected. And recovered people always stay recovered in this model. Moving on. The transition rates from being susceptible to infected is proportional to the number of infected people. Because the more infected people there are, the more likely you are to be infected, and obviously the time step as well. And the proportionality constant is called the infection rate. Meanwhile, the transition rate to recover is a constant multiplied by the transition time step, and this is called the recovery rate gamma, this proportionality constant. So how did we implement ECS? Well, it was quite intuitive. We basically all of our people and members of the population were represented using entities that had three components. So one component was their state, which could be susceptible, infected, or recovered, which was given 1, 2, or 3 respectively. They had an index which was useful for saving the data to a data file, and then they had transition probabilities, which depended on their current state, the current state of the system. Then there are systems, the systems we had which contain all the behavior. We had 2 systems. One of them updated the state based on their transition probabilities. So in this example in the diagram, so a person who's initially got state equals 1 means they're susceptible. At some later time, they become infected in the next time step, and so their state is now 2. It was the system that did that. Then there was the update transition probabilities. Once you're in a new state, then your transition probabilities will need to be updated to reflect that. So what are the results of this? Doing an ensemble averaging, we had 100 samples and we used an infection rate of 7/n, where n equals 100 is the total population, and we had a recovery rate of 1. Then we had in our first one, we had 1 person who was infected, and we saw that most of the time everyone got infected, but sometimes basically no one got infected, and so we had a large deviation. And in the second one, 10 people were infected, and we saw that pretty much everyone got infected, so it was a much smaller standard deviation. Next slide. So what was some further work we did? Well, we looked at different compartmental models, like the SEIR model, where we have someone who's infected. The exposed category, someone's infected but not infectious. We looked at network models where people who are connected on a network can infect each other, otherwise you can't. And we looked at spatial models. In particular, we looked at a spatial plant epidemiological model, which reflected new research. Next slide. So what are our ECS takeaways? Well, we found that it was suited to epidemic models where we had many entities with similar behavior, and we found that it was easy to extend epidemiological models, like adding new categories.
Okay, so the conclusions are that this gives some early results that suggest ECS may be useful for exploratory simulation by early career research, ECRs basically. It's genuine research. The students actually won't be on the literature they surveyed. The HUD work is much more detailed, which isn't covered. There's in the follow-on slides at the end, backup slides. There are open questions. Does it generalize beyond this one case study? What problems suit ECS best? Got disease outbreaks, epidemiology, fluid dynamics. There's probably many, many more domains. And energy awareness is something that can be built into this by default, so can this become normal? Lastly, I'd like to thank Oluwole and Mattias for their efforts on this project. The fact they produced some really interesting, genuine research beyond the literature was a particularly good result. And finally, thanks to the organisers for organising such a great event.
Thank you. Do we have any questions? Looks like we don't. So we'll move on to the next speaker, which is Mr. Raman Dandoy.
Yes, I'm here.
Yeah.
All right. All right, here. Hello.
Hey, we can hear you.
You can hear me perfectly?
Yeah.
Can you see my screen?
Perfectly. Yes.
Yes. Perfect. Great. All right. Can I start?
Go ahead, please.
All right. So, hello everyone. So, my name is Raman, and I'm a student here at CERN, a technical student. And as part of my master thesis, I am working on life cycle assessment of the LHCb data centers. So in this presentation, I try to be as straightforward as possible, considering the time constraint, but please do not hesitate to reach out either during the question and answers right after or by mail if you have any other questions. So, as you probably know, there are a couple initiatives that have been going on recently, trying to identify and to tackle environmental impacts in HEP recently. So this definitely manifests the need and envy of the community to solve those environmental issues due to some HEP activities. So my work, my master thesis, this first part, if I manage to, sorry. All right. This first part of my work, so really is in the scope, so the life cycle of assessment of the LHCb data centers. So here you have a fully detailed, let's say more or less fully detailed overview of the details of this life cycle assessment. What is important to understand is the scope of this study. What am I talking about? So I am talking about the LHCb data flow. So from the data which are generated from induced from the collisions, so in the detector, and which are then sent by optical fibers to the data centers of LHCb on site in France. Those data are going through the event building and some filterings, so the high-level triggering 1 and 2. So these first filters leave us with some data which are then sent globally. So to universities, national centers, and for further processing, basically, so for Monte Carlo simulations, for example. Here in this presentation, I will just go through mainly the climate change impact, so in terms of kilo of CO2 equivalent. There are other environmental impact theories which are very important too, but I'm lining up with certain environmental reports right now, so I will only focus on this. All right, so here are some challenges that I faced, knowing the methodology, which was very hard to find a standardized way of assessing those impacts for data centers. There are some ISO recommendations, so ISO standards, but these are more KPIs rather than real functional units, like ready to use. So instead of defining one, because it was pretty hard, I decided to compare like the results with the experiment itself. So comparing the results with the integrated luminosity. For the data, it was also a bit hard because so EcoInvent, which is like the mainstream database for LCAs, is not super well adapted for IT components, for IT hardware. So for this, I've been using Resilio database. And for the offline grid, this is also quite of a challenge because this represents a globally distributed so infrastructure, many infrastructures actually, data centers. So this is really hard to get the hardwares of every one of them. So for this, I managed to like assess the impact of the electricity consumption, but for the embodied, I am currently working on it. But so in this work, this is still excluded. For the methodology, if you are interested, there is a really nice paper which has been brought by some researchers from EPFL, Giulia Paolini and Xavier Ricouvrard, which have brought quite a new way of assessing data centers impact. And for the infrastructures, we have some people working here at CERN on solving those problems. And I mean, I really invite you to check this out. All right, so here are the first results. So here, in order to compare the different components of one data center, so for the embodied, you have to normalize it. So here you have an annual impact. So you basically estimate a lifespan for every one of those components, and then you take the total of their impacts and you divide. Then you have more or less an idea of the impacts from one component to another. So this gives us this diagram, which is pretty clear that the main contributor here are servers. And the picture doesn't change much more when you are adding the operational impacts. So here the operational impact being basically the electricity consumption. You can see that, okay, the embodied is still the biggest impact, which is kind of unexpected. I explained this with two reasons. So because LHCb sites, but CERN in general is using the French electricity mix, so mainly nuclear, so low carbon. This might be a first reason. And the other one is the excellent PUE of our data centers at LHCb experiment, 1.05. So if you have no special benchmarks in head, I give you this little graph where you can see that this is very, very abnormally good. But still keep in mind though that these are models, so these are inherently these has uncertainties. So this has to be kept in mind, definitely. All right. So for the offline part, here you are looking at a map of the LHCb, so the global distribution of offline computing for LHCb for the year 2025. So as you can see, this is mainly dominated by Switzerland and UK. Switzerland, because of course, this is like CERN tier 0 anyway. And this helps me actually to then provide you this. So on the left, you can see that the electricity consumption of the online, so meaning really the LHCb sites, is higher than the offline. But when you compare to the carbon impact, this is the other way around. So we are discussing about potentially relocating some of jobs from the offline to the online, especially here during this long shutdown period, which is coming to avoid basically those emissions. And here you have the formula that I've been using to get those results. As I said, all data are not always readily accessible. So for the PUE, it's just a mean. And for the core energy, the 3.8 that I've been using is from also some colleagues here in CERN that have been doing some measurements, actually. For the carbon intensity, I've been using electricity maps, basically, and all the sites are based on location-based intensity, except for CERN tier 0, which is based on market-based, which is not like 100% accurate, in fact, of course, because some of their sites have like photovoltaic panels, for example, or have like green contracts for renewable energy and everything. But okay, I had to find a way to start the study. So this is the start, but of course, after it would be better to include these. All right, so here comes the second part. So the upgrade tool. So for in a couple of years actually now. So here are the preliminary results. So for the Velo and for the Muon. So the idea here is to have find hotspots for the different subdetectors of the LHCb, and then try to find some leverages. If there are some, it is of course very difficult to find leverages in such infrastructures which require like few tolerances and which are very complex. So this is very hard, but I will try. And as from the previous talk, I mean, the first step is of course to try to assess this, and then we will see. Anyway, from those preliminary results, you can see that, of course, the hotspots are already different. So this is from the PFC used in MIO, which is the main impact. And from the velo, this is the structure, basically. The global methodology I am using is to start first with the current configuration of the detector, and then try to understand what are the changes which are going to be applied for upgrade 2. And definitely after this, try to find some leverages in through a detailed breakdown of those components. So why does it matter? Because those changes are upcoming and we can still act now. So this is sometimes kind of rare, I feel like, in this field. So this is great because we can technically still act on some things. And yeah, this is kind of it. And as I said, it's the first step to try to assess this, and then, if possible, try to reduce our footprints. Thank you for your attention.
Thank you. Oh, perfectly on time. So do you have any questions? Yeah, Claire?
Yeah, I guess. Thanks. That was a really interesting presentation. When you were talking about you're looking at, or LHCb is looking at using more of the online system for offline analysis, will you?
Sorry, excuse me. I think excuse me. I mean, okay, here. Sorry, excuse me.
Will you also be able to use, make full use of the GPUs?
Sorry, you are mentioning, like, do you have a slide in mind, like
Exactly
or
this one actually.
this
Yeah,
one?
because you were saying that LHCb is looking at using the online, online processing servers for offline during the long shutdown.
Yes. I mean, so in any way, actually, online was planning on doing some simulations to relieve from some work from the offline. In any case, this was planned anyway, but we are talking about maybe increasing like the work actually. Yes, dedicated to the online. Yes.
Mm-hmm. And also making use of the GPUs.
Yes.
Mm-hmm. Okay.
Yes, exactly.
Any other question? In that case, I'll thank the speaker, Roman, and we'll move on to the next speaker, and they'll be the last speaker for the conference. May I invite Jesica Sabau for on the talk of carbon aware scheduling for sustainable computing.
Can you see it okay?
We can see your slide, but it's in the vertical.
Oh, right. Is that all right to keep it like that for now?
It's all right. It's fine.
Yeah. Okay. Perfect. Yeah. So, hello everyone. Thank you for having me here. My name is Jessica. I'm a student from the University of Sheffield, and we also have Kristen with us here today, who has been my supervisor for this project. And so what today's talk is about is just some early work on carbon-aware scheduling. So specifically a lightweight scheduler, which I created called the Sustainable Queue, which delays ATLAS workloads from to a lower carbon window. So to motivate this, energy consumption is generally directly proportional to carbon dioxide emissions at a given carbon intensity. And this carbon intensity fluctuates significantly based on the energy source mix at that specific grid. We know that the WLCG consumes about 1.25 terawatts hours a year during the Large Hadron Collider runs. and the jobs produced are just dispatched immediately when the resources are free, regardless of the current energy mix. And so this talk focuses entirely on just can we use this variation to reduce the carbon footprint of ATLAS computing workloads. So this simulation is deliberately simple. There's no machine learning involved, no sort of carbon forecasting. It responds only to the current carbon intensity of the local grid and built entirely on public real-time grid carbon data. And as I mentioned before, it's just to test whether the emissions can fall without changing the WLCG infrastructure. There are two ways you could reduce this carbon footprint of the workloads. First is temporal shifting, which is just delaying jobs in time to run when the green grid is cleaner. And that's what today's work is focusing on. We also have spatial routing, which is moving jobs to different sites with a cleaner grid at that moment, which isn't considered in this talk today because it's a separate problem with its own challenges, such as data locality and site availability. So this is just a little flow chart of the logic. So we have flexible jobs entering this queue. We don't include tier 0 jobs in this simulation because these run on a 24-hour reconstruction loop for data calibration and data quality monitoring, which just can't be delayed. And so every job is rechecked against each hour, against 4 tiers, sorry. So if it's weighted under 12 hours, it only runs if the carbon intensity is below the 25th percentile. We then have another tier, which is between 12 to 24 hours. The job will run if it's below the 50th percentile for the carbon intensity. We then have the tier in which we have hours or jobs between hours of 24 to 48 hours. They only run if the carbon intensity is below the 75th percentile. And then we have sort of a maximum delay parameter of 48 hours. So if any job has been waiting for longer than 48 hours, the job will be run regardless, which is just to make sure that the physics program isn't disrupted. One important detail is that these percentiles are calculated per grid for each country. So from their own annual carbon distribution. So there's no sort of single fixed threshold we use here, and that means the scheduler automatically adapts to the local conditions. So yeah, as I mentioned, it's a simple simulation, just based in Python. I use libraries such as pandas and NumPy for data processing and percentile calculations. And within the simulation, there are sort of 2 main input sources. First being the carbon intensity data, which is from just national energy data platforms. This data is given in watts. And then we also have the ATLAS job workloads, and this is typically given in HEP score 23. And so because we have these 2 different units, I created a conversion factor, and that's just using an ATLAS default of 10 watts per core. And I divided this by a typical site score of 20 HEP score 23 per core, and that gives us a value of approximately 0.5. So yeah, in this project, I primarily looked at 2 contrasting national grids for a full year in 2024. First country we see in the orange is more weather driven by wind and solar, despite having other energy sources such as coal and other non-renewable sources. And this wind and solar energy produces large daily and seasonal swings in the carbon intensity. We then have country 2, which is more flat due to its dependence on nuclear energy. So it's consistently low, narrow range carbon intensity year round. I picked these deliberately. Country 1 tests whether the scheduler can really capture real savings when there's a strong signal to exploit. And the other just shows how it behaves when there's barely any signal at all. Now, this project isn't just about the present. It's also about studying and stress testing future scenarios. So I ran 4 scenarios, which is designed to isolate 2 variables independently, which are the cleanliness of the grid and the CPU capacity available. So just looking at the 4 scenarios that we have, scenario 1 is sort of baseline for this project. incorporates the 2024 grid and the 2024 CPU capacity. Looking at scenario 2, we use the 2030 grid target, which was just calculated by using the published 2030 renewable targets from each respective country. And then we keep that same 2024 CPU capacity. Scenario 3 uses the 2024 energy grid and the CPU capacity multiplied by a multiplier of 1.5. I should mention that the CPU capacity in this project is an assumed approximation, which is just 1.1 times the observed peak demand. And so that just gives the scheduler headroom to delay the jobs rather than just running fully saturated. And then lastly, scenario 4, which is incorporating both these 2030 energy grid targets and the multiplied CPU capacity. It's also worth noting that these scenarios aren't just useful for situations where you're trying to save carbon. The same logic applies to situations where you need to reduce the energy usage because there is less energy available. And that availability is volatile or varying. And the scheduler doesn't really need to wait for a better window. The mechanism just generalizes energy scarcity conditions just as well as it does to carbon reduction ones. So by looking at the results, firstly for country 1, we see that across all 4 scenarios, we have reductions between 20.7 to 29%. And if you look specifically at scenario 2, we can see that the best case scenario is that is the best case scenario, and it saves approximately 784,000 tons of carbon emissions in a single year. And then we compare it to country 2. Same scheduler, and we see that throughout all 4 scenarios, we have a reduction between 10.3 to 12%. And this is half the relative impact compared to country 1. So yeah, as I said, it's the same simulation. The reason, or one of the main reasons potentially for this change in reduction could be the variation within the carbon intensity. Another key result, which I found quite counterintuitive, was that more hardware does not mean more carbon savings. So if we look specifically at country 1, in the scenario where we decrease the CPU capacity alone, we have savings of about 711,000 tons. Whereas if we look at the scenario where we just increase the renewable energy alone, we have a saving of about 784,000 tons. And the reason for this is just that the scheduler prefers sort of backlog. So more compute clears up the queue too quickly, and the backlog needed to wait out dirty window never gets a chance to build up and escape those dirty windows. And so for the more volatile decarbonizing grid, we have more frequent clean windows in which the queue can exploit. The key takeaway from this is that grid decarbonization and the hardware investment sort of need to be planned together instead, and they shouldn't be assumed to help independently. I will flag one caveat here, which is sort of directly related to this. In the simulation, the jobs are treated as clearing more or less simultaneously once this sort of slot opens up, rather than modeling realistic execution durations. And that simplification is part of why more hardware looks this decisive in these results. And it's exactly kind of the detail why we need more realistic modeling before we treat this finding as final. And so, yeah, that's why more detailed investigations are needed to understand these dynamics properly. There are a few limitations involved with this project. Firstly, like we mentioned before, these tasks are instantaneous, and the study doesn't account for the realistic job execution durations. Secondly, we have all of this generated electricity is treated available for compute only and ignores other grid consumers. Then the conversion factor obviously does vary site by site, depending on the country and the grid, or just mainly the country, sorry. And a single year of data doesn't capture long-term weather variations. So, for example, country 1, which was more volatile, variations in weather could cause deeper fluctuations or longer fluctuations. The energy consumption of the idle hardware isn't considered, as well as the embodied carbon from hardware isn't included, and this becomes more important as the grid cleans up. And as mentioned before, the CPU capacity is 1.1 times the observed peak demand. So overall, the results just show that a lightweight scheduler can produce real results, but this sustainable queue isn't a complete solution to the environmental footprint of high energy physics computing. But it shows that this lightweight approach can produce real results, and as grids across the world continue to incorporate more renewable energy, the conditions under which temporal shifting works best will only become more common. Thank you. Sorry.
Yeah. Thank you. Floor is open for questions. So one question from you. Are you planning to continue this analysis? Because you have mentioned that it was done for a limited time and it may not encapsulate the whole variations which may come across. So are there any plans?
No, unfortunately, I won't be, as this was my sort of third year project, and I'm going into my fourth year next year, and I'm doing sort of slightly different projects. However, there is a student at the University of Manchester, which I recently had a conversation with, that is planning to sort of touch up on this sort of project and look into it in more detail. Yeah.
Okay. Are there any other questions? Oh, we have one from Michael.
Yeah, my question is, you talked about more computes doesn't necessarily solve the problem. And I thought that was really interesting. I just wondered if you could expand on that particular point that you raised on that slide.
Yeah, let me just go back to that slide. So yeah, I found it quite counterintuitive when I found it out as well. I just assumed that the more hardware we have, sort of the more jobs would be able to run faster, or just produce most savings. But because of the assumptions that I used, so for example, creating the jobs is sort of instantaneous, and those sort of assumptions, the way that the scheduler behaves is that it prefers having that backlog because it then has more sort of jobs in which it can then delay to bring into cleaner window, if that makes sense. So the more backlog we have, the better the results typically are. Yeah.
It's really interesting. Thank you.
Thank you.
Any other questions? So with that, I'll thank Jesica again, and we'll move on to the closing session. I'll share my screen. So my slides are visible, right? Okay.
Maybe not a full screen for me. I don't know for others.
It's not full screen?
No, it's okay.
Yeah, okay. So we have reached the end of 5th edition for Sustainable HEP and spanning 3 days. And before we wrap up, we want to take a moment to reflect on where we have been over these past few days. So we have had 4 plenary speakers who set the stage and gave us a big picture. I would like to quote one instance from Professor Archana Sharma's talk, where she said that our physics goals have changed over time and they should be kept changing. So in 1970s, we used to ask how can we, if our detectors can detect precisely. Then we asked if our detectors can survive the high LUMI LHC. But now it's time that we ask that if they can survive without harming the environment. We also had close to 26 submitted talks on 3 themes.
Sorry, is it only me or the slides are not shifting on Zoom?
The
Same
slides
here.
are not changing.
It could be a lag.
We
No,
are
it's not
still
a lag.
seeing the first slide.
Oh, no. Okay.
Now
Now
it's
they've
now
changed.
it's the submit. Yeah, great, thanks.
Right. So I moved on to this. Then I had moved on to my third slide. All right. So we had 26 talks on 3 themes: large-scale project and policy making, better materials and sustainable detectors, and sustainable computing. Slide 4.
Yeah, now we can see them very well. Go ahead.
All right. Okay. We also had a panel discussion on careers from physics to sustainability. There are many different career paths open to those who have background in physics, including to more sustainability-related careers. These can look very different even within the definition of sustainability. On Thursday, we heard from 5 fantastic speakers, and they shared many insights into their career transition skills they have acquired while they were in physics. There were many great takeaways, but if there is one line summary, it would be to be curious, and there is no one career path. It is possible to incorporate sustainability into your existing work or to shift your career towards it. Personally, what struck me across all these sessions is that sustainability in high energy physics isn't a single problem with a single fix. And again, coming back to Professor Archana, so it spans the policy decisions that shape how our large collaborations and facilities are planned, the computational choices that determine the energy footprint of the data we process, the physical materials and detector technologies we choose to build our experiments with. And each of these areas comes with its own challenges and its own trade-offs. In its own community working with its own community working hard on to tackle these problems. We also had sessions by the
I'm sorry, Chandramouli, we are again seeing slide number 4.
Okay, so this was slide number 4.
Yes, we were at here, and
then I moved on from here, and then I said that we had fantastic session by Ben Shepherd, which most of the people liked. He talked about various. He and some of the other speakers talked about the analysis, the sustainability assessment that was done on large projects. There was sessions on sustainable computation, and finally there were varied efforts from large scale to smaller projects, efforts in sustainable materials, computing, and more. Growing number of projects and efforts has been done since the first edition of Sustainable HEP, which was in 2021. And since then, this has been a growing and fantastic community. There are also other sustainability initiatives if anyone is interested. There is Sustainable HECAP Plus initiatives. We have Open Research Lifecycle Assessment Project. There's CERN Alumni Sustainability Group, Plastic Fresco, and initially we got introduced to a new initiative, which was and the founder had the talk in this edition, which is released at CERN. And for the future communication, all the talks, all the sessions were recorded, and they will be uploaded on YouTube as soon as possible. In fact, days 1 and 2 are already there. For further discussion, we are always, and the community is always available on Mattermost. And please take your time to give us the feedback so that we know what to improve and to reach more people with this initiative. So an important logistical note, this is the first time in Sustainable HEP series that we'll be publishing proceedings on SciPost. If you have given a talk, it'd be really encouraging for you to pursue this opportunity to write up and further disseminate your contribution. You can find more details on the Indigo page. I'm mentioning a few. So the submissions are capped at 4 pages. It includes the title page and not the references page. And the deadline is 30th September 2026. There's plenty of time, but so it's better to get move on. Then this was the conference photo. You can take this from the Indigo page. And thanking to those who made the wheels move. We have John Adams Institute for Accelerator Science, Royal Holloway University of London, and Department of Physics at University of Oxford. And of course, we have CERN. And a big shout out to all the organizers. We had Shreyasi, Jan, Kristen, Hannah, and I, Chandramali. And it could be your chance to help organizing this conference for 2027 edition. So please do reach out and mail us if you have any query, and we look forward with working with you. And finally, that's it from us. Thank you, and we hope to see you in future editions of Sustainable HEP.
Thank you.
Thank you, everyone who joined and participated. And if anybody else wants to say something, did not have the chance to say during the meetings, the floor is open. Something quick, something, you'd like to share with us if you have.
I think people are tired with the long day.
Okay. This is Friday, and thanks a lot everybody for staying with us throughout this journey. Hopefully see you all next time, and we keep in touch through Mattermost and emails and everything.
Thank you. Bye-bye.
Bye-bye.
Bye.
Bye.